Hey everyone, so today I'm going to be doing a video on elastic and inelastic collisions. This is still to do with force and momentum, and if you don't know about momentum and even about kinetic energy, go to my previous videos and look for information on those, because otherwise it's going to be a little bit hard for you to understand these collisions, okay? I'm also going to put that video there on the link in the description. Oh, I just said I'm going to put the video on the link. I'm going to put the link of the video on the descriptions so you can see that that YouTube video that has examples of elastic and inelastic collisions and tells you what happens. I think it's just a good summary. So, collisions, you can have elastic or inelastic collisions. Now, think about the collisions of hard steel balls with the Newton swinging ball. So the Newton, oh, I forgot the words. Oh, I'm just so tired. The Newton crane, is that what we call it? They are nearly elastic. They keep going and touching each other and then making the other ball to move away and all these things. So they are kind of bouncy. So any bouncy collision, like this one here in the diagram, is going to be an elastic collision. Inelastic collisions, they are different. It's like if nothing there is elastic, meaning that something collides and then it just stays there. It carries on. So the two things move together, for example, okay? So that's the example of inelastic collision. Now, in terms of mathematics, what happens is in an elastic collision, momentum is conserved. Momentum is conserved in all collisions, really. And then if my collision is elastic, then the kinetic energy is also conserved, okay? Now, if I have an inelastic collision, then momentum is conserved because, of course, it's a collision and momentum is always conserved. However, the kinetic energy is not going to be conserved, okay? So that's the difference, mathematically speaking, between elastic and inelastic collisions. In elastic collisions, there are going to be no dissipative forces acting during the collision. So all the kinetic energy of the objects before the collision is still in the form of kinetic energy afterwards. But with inelastic collisions, that doesn't happen. And I think I have I have it here. In an inelastic collision, then part of the kinetic energy is going to be changed to some other form of energy in the collision, okay? And I have here, again, an example. I have the blue and the green ball. Before, the blue ball is going towards the green. After, the blue ball and the green ball get stuck to each other and they keep moving, okay? So momentum is conserved in all inelastic collisions, in fact in all collisions, okay? But you cannot track what the kinetic energy through the collision is doing because it's going to go to other forms of energy, sound, heat, for example, okay? So if you think about it, in reality, any macroscopic collision, so anything in the real world, is going to be it's going to have some of the kinetic energy that the objects had before is going to be converted into internal energy or any other forms of energy. So to be honest, in reality, or if you just think about anything that is a large-scale impact, they are not perfectly elastic, but we can say that they are just for a certain calculation to make it easier. But in reality, some kinetic energy is always wasted, okay? And I don't like to say wasted, it's converted into another form. So let's look at an example. I have a railway wagon, I'm not normal today, of mass of 8,000 kilograms, is moving at 3 meters per second, and it collides with an initially stationary wagon of mass 5,000 kilograms, and the two wagons separate after collision. The 8,000 kilogram wagon moves at a speed of 1 meters per second without a change of direction after the collision. So they want you to calculate two things. Number one, the speed and the direction of the 5,000 kilogram wagon after the collision. And then number two, the loss of kinetic energy due to the collision. So let's do these questions. So let's go in number one first. Of course, you know, pause the video. Too late now. Pause the video if you want to try them beforehand, okay? So the speed in the direction of the 5,000 kilogram wagon after the collision, that's what they want. I'm going to use the conservation of momentum formula and go to my previous video if you do not know what I'm talking about. So m1 times initial velocity of 1 plus m2 times initial velocity of 2 equals m1 times the final velocity of 1 plus m2 times the final velocity of 2. So I'm going to consider my object 1 to be the 8,000 kilogram wagon. So I get 8,000 times 3, the initial velocity, plus 5,000 times 0. The other wagon was stationary. That's going to be equal to 8,000 times 1, because that's the final speed, plus 5,000 times v, because I don't know what v is, okay? So if I do the calculations, I get 24,000 plus 0 equals 8,000 plus 5,000 v. Okay, so I get 24,000 minus 8,000 equals 5,000 v. Therefore, I get 16,000, one taking away from the other, divided by 5,000 v. So yeah, that's equal to v. So v equals 3.2 meters per second, and I know that is in the same direction as the first wagon, because I decided that the velocities were positive, and in my result my velocity is positive as well, so it means that the vector is going in the same direction. Going on the second question, what is the loss of kinetic energy due to the collision? Well, the loss of the kinetic energy is going to be the difference between the kinetic energy before and the kinetic energy after. So before, using the formula that says 1/2 times the mass times velocity squared, I have, for the first wagon, 1/2 times 8,000 times 3 squared, which gives me 36,000 joules. And for after, for that wagon is going to be 1/2 times 8,000 times 1 square, which is 4,000 joules, okay? And then for the 5,000 kilograms wagon, 1/2 times 5,000 times 0 squared, which is 0 joules, so no kinetic energy initially, and then 1/2 times 8,000 times 3.2 squared, the velocity that I got after, which gives me 25,600 joules. So what I'm going to do is, I'll look at the energy before, which is this plus this, so 36,000 joules, and I minus the total energy after, so 4,000 joules plus 25,600 joules, okay? And if I do the calculation, I get 6,400 joules, okay? So that's how you get the answer. So that is it for today on elastic and inelastic collisions. I'm going to add the link into the description. And yep, up to then, be happy and healthy. If you have any questions, just let me know. Bye!